The electrical grid is the interconnection of several generating stations together in a network in parallel. That is, the electrical energy that is generated in thermal power stations, hydropower stations, nuclear power stations and wind power are connected to a common network in parallel before it will be further transmitted via transmission lines to power substations, and to the final user down the chain of transmission.
In generating station, the generated voltage is usually between 6 kV and 11 kV before it will be further stepped up to as high as 330 kV or more. The voltage range is a function of the grid rating voltage, so it can be more than 330 kV or less. The reason why the generated voltage coming from the synchronous generator is further step up is to prevent line losses, which is because the generated electricity will be further transferred over a long distance before it reaches the grid for termination to the network.
That said, there are some conditions that must be met before the generated electric power can be interconnected together in a grid system. These conditions are root mean square voltage, frequency, the phase angle, and the waveform to that of the grid which is being synchronized. So in layman's terms, the voltage of the generator must be the same as the voltage of the network. That is, if the network voltage is 190 kV, then the generator voltage must be 190 kV before synchronization can be safely done. Also, the frequency must also be the same.
So in a nutshell, before synchronizing the generator with the grid of other generators, the AC generator must additionally matches in its timing. This timing of the frequency and the voltage rating of the network being synchronized too. This requires both the speed and the excitation to be systematically controlled for synchronization. This extra complexity was one of the arguments against AC operation during the War of Currents in the 1880s. And these can be proved using this formula here. N is equal to 120 multiplied by frequency over the number of poles, where N is equal to the speed of the rotor, F is the operating frequency of the generator, and P is the number of poles of the generator. In our case here, the frequency will be fixed. That is, it should either be 50 Hz or 60 Hz, and the speed is equivalent to the poles of the motor. That is, the speed or the number of poles should be varied accordingly in such a way that the frequency gotten is within the desired range that is needed before synchronization.
In power stations that are driven by steam turbines or gas turbines, this power station usually uses an impulse reaction type turbine to convert fluid flow to mechanical energy. This power station operates at a higher speed of between 3000 to 3600 revolutions per minute. Hence, the structure of the generator is a non-salient type which usually has between 2 or 4 pole field windings.
In order to confirm what you said, we can quickly work out the working speed that will give us the required frequency for synchronization. 120 multiplied by 50 Hz all over 2. This will equal to 3000 revolutions per minute. Likewise, the same calculation can be done for a gen set operating at 60 Hz. That is 120 multiplied by 60 Hz all over 2. This will equal to 3600 revolutions per minute too. The same calculation can be done for a generator set that has 4 poles too. So at 50 Hz, the speed should be around 1500 revolutions per minute. And at 60 Hz, the speed is 1800 revolutions per minute respectively.
In the same vein, in power stations that are driven by hydraulic turbines as in hydropower, the hydraulic speed is very low, which is usually between 80 to 375 revolutions per minute. This is because of the large salient pole generators with pole size numbering as high as between 24 poles to 48 poles.
With these specifications, We can also calculate the speed that the power station will be operating in when the number of poles is 24. Which we can work out as 120 multiplied by 50 Hz all over 24. This will equal to 250 revolutions per minute. Also, if the same calculation is done when the required frequency is 60 Hz, the speed will be 300 revolutions per minute. Likewise, when the number of poles is 48. The speed can also be calculated as 120 multiplied by 50 Hz all over 48. This will equal to 125 revolutions per minute. At 60 Hz, the speed will be 150 revolutions per minute. So overall, we can also calculate the number of completed cycles within a specific time. That is because an alternating current is an electric current that periodically reverses direction and changes its magnitude continuously with time. Using period and frequency formulas. Period is equal to 1 over frequency. The time taken to complete one cycle is 1 second divided by the total cycles, which is 50 Hz. This will equal to 0.02 milliseconds. So for every 0.02 milliseconds, a cycle is completed. And for every 1 second, we will have 50 completed cycles.
In addition, before I will continue to look at the remaining conditions. When the frequency is not up to the required value that is needed before synchronization, the generator is brought up to approximate synchronous speed by supplying more energy to its shaft. For example, opening the valves on a steam turbine, opening the gates on a hydraulic turbine, or increasing the fuel rack setting on a diesel engine. Now that we have known the intricacies of frequency, the other conditions are the phase sequence, phase angle, and waveform.
Waveform and phase sequence are fixed by the construction of the generator and its connections to the system. During installation, careful checks are made to ensure the generator terminals are done correctly so that the order of phases matches the system. Connecting a generator with the wrong phase sequence will completely damage the generator or other generator that is already connected to the system, because the system voltages are opposite to those of the generator terminal voltages. Finally, the phase angle, which is the phase shift that exists between voltage and current, must be the same for the generators and grid to be synchronized with.
Now, the synchronization between the grid is done automatically via power automation. The controller checks if the parameter conforms with the grid specification, and if those parameters match the parameter of the incoming power supply from another power station to the grid. If it matches, the new generating station will be automatically added to the grid, thereby allowing the generator to be synchronized to the grid.
However, before this time, power synchronization is done through the use of 3 incandescent light bulbs. The 3 incandescent light bulbs will be connected between the generator terminals and the system terminals. As the generator speed changes, the lights will flicker at the beat frequency proportional to the difference between generator frequency and system frequency. When the voltage at the generator is opposite to the system voltage, the lamps will be bright. When the voltage at the generator matches the system voltage, the lights will be dark. At that instant, the circuit breaker connecting the generator to the system may be closed, and the generator will then stay in synchronism with the system.
The grid is the backbone of any nation's electricity supply. This complex network of electricity substations, transformers, and power lines is responsible for transporting electricity from the generation station to the end user for consumption, and everything else in between. There are 5 major benefits of electric grids. These are: exchange of peak load, use of older power plants, increased diversity factor, reduce plant reserve capacity, and economical operation.
Starting with the exchange of peak load, when there is high demand coming from the consumer end. Excess load can easily be shared by other stations interconnected within the grid. That is because the grid is interconnected with other power stations. Another area is that it allows the use of older power plants. That is, plants with lesser capacity can be relied on during the off-peak period while giving room for energy conservation and maintenance work. The diversity factor of the grid can be improved through the use of diversified energy sources and load distribution. That is, by incorporating a mix of renewable energy sources such as solar and wind, which limit the dependence on a single source of energy, hence, it improves the diversity factor of the grid. The third point is that it reduces plant reserve capacity since several power stations are interconnected in parallel, and the reserve capacity of the system is reduced, thereby increasing the efficiency of the grid. Lastly, in terms of economic operation, it increases the economical operation of the grid, which is done through load sharing. This method allows power to be supplied by the most efficient to the least efficient plant in order to reach peak demand.
Overall, the grid helps in balancing out fluctuations in supply and demand, which will improve the overall reliability of the electricity supply in the long run. Additionally, connecting power stations in a grid can enable more efficient use of resources, as it allows for the integration of different types of power generation, such as renewables and traditional fossil fuel-based plants. This resource utilization provides redundancy and resilience in case of outages or emergencies, as power can be rerouted from other sources. Overall, a connected grid can lead to a more stable, cost-effective, and sustainable electricity supply for consumers.
Before we look at the substation proper, people will naturally ask if it could have been possible to connect all the load from the consumer end directly to the generating station without going through the substation. To find out more if it is possible, kindly check the upcoming second series next. And that is it for today's series. I hope you have learned something new today. See you at the next one.